Okay, this is the third video on Aldol reactions. In this case, I'm going to look at some example problems. So in this first example, we want to predict the condensation product and then draw its mechanism. Now, I've broken this problem up in a couple slides. On this first slide, I just want to predict the condensation product. Now, the book has one way of doing this in the solutions manual, and I didn't like that as much. So I've got a slightly different way of doing it. If you don't like my way, check out how he does it in the solutions manual. Maybe you'll like that way better. So what I like to do is first figure out what my addition product is, and then figure out what the condensation product is. And so to find the addition product, right, I want to draw the enolet that's going to be attacking this thing. Right, so I've removed one of the alpha hydrogens, and so what's going to happen is my enolet's going to attack the electrophilic carbon of the carbonyl group, and then this is what's going to become the alcohol. And so to think about the addition product, right, I'm going to form the alcohol, and then this is the carbon that attacked it, right? So I'm forming a new bond between this carbon and the carbon that's now the OH. So that's the new bond that I formed. And then coming off that carbon, so this carbon that was part of the new bond that was formed, I have the aldehyde going one way, and then going in the other direction, I'm going to have this tert-butyl group. And so that's my aldol addition product. For the elimination, I'm going to get the double bond here, and then I need to decide which of the two isomers am I going to get. And so what I kind of do is say, okay, so we're going to eliminate the OH, and we're going to get the double bond here. So that would be one of the possible alkenes that I would make, but I want to make the less sterically hindered alkene. And so this tert-butyl group is going to be bumping into, whatever the name of this thing would be, and then this smaller group than the tert-butyl is going to be bumping into the hydrogen here. And so I want these two groups to be trans to one another to give me the least steric hindrance. And so to draw the final so then I want the aldehyde going down so that the tert-butyl is on the opposite side of the double bond as this big bulky group. And so this should be my condensation product. All right, so now we want to draw the mechanism. And I think it's easy to break the mechanism up into two pieces. So first, draw the mechanism for the formation of the aldol addition, and then we can draw the mechanism for the elimination that's going to give us the condensation product. So the first thing that we need to do to form the addition product is I need to use my base to pull off one of the alpha hydrogens. And so that's going to give me this carb anion. And then this is going to be the nucleophile, and it's going to attack the electrophilic carbon of my aldehyde. Kind of a funky curved arrow there. That's going to give me almost the addition product, except we need the last step to protonate that oxygen. And so that is the mechanism for the first part, right? So we've made the addition product. Now on the next slide, we'll finish the mechanism by drawing how I get from the addition product to the condensation product. Okay, so the last part, eliminating the water to give us the condensation product. I need to show the alpha hydrogen here. So my base, pull off that alpha hydrogen, leaving us with the lone pair on that carbon. And then the last step is just the loss of the leaving group. And that'll give us our condensation product. Okay, here's another example. And we want to predict what the addition product is going to be when the following aldehyde is treated with aqueous sodium hydroxide. So again, I like to think about, all right, this is my alpha carbon. So we have one hydrogen here that we can pull off when I form the enolet. And so that is going to attack here. And so this is where the OH is going to be. And so then I usually start by drawing where the OH is. Might as well leave the hydrogen off because it's just going to get in the way when we're trying to draw this. And so I've got a new bond between this carbon and this carbon. So let's draw that bond, and then we can draw what's coming off that bond. Right, so now what's coming off of this bond is the six-membered ring. Or not coming off the bond, right, but what's coming off this carbon is this part of the six-membered ring. So I've drawn as part of the six-membered ring, and then it also has the aldehyde coming off. And so this would be our addition product in this case. Right, now they didn't ask us, but we couldn't draw the condensation product because in order to have the condensation, I need to have another alpha hydrogen, which I don't have. And so in this case, I can't form the aldol condensation. I can only form the aldol addition product. All right, in this problem, we want to identify the reagents that can be used to produce the following compound. I have another similar example on the next slide. And so this gets down to the crossed aldol reactions. And so I want to see what are the two aldehydes and ketones that I need to react. And then if one of them can't form the enolet, then I can just react those two compounds with sodium hydroxide. Or if they can both form enolets, then that's where we need to use LDA and do the directed aldol addition. So our first task is to see what are the two compounds or the two aldehydes and or ketones that we're reacting here. And so this is the ketone that I have left. So this is the alpha carbon that attacked the electrophilic carbon in the other compound. And so this is the new bond that we formed. And so the two compounds that we had to start with were this ketone and this aldehyde. Now, this ketone is obviously the one that we turned into the enolet because it's the one that did the attacking. This aldehyde only has one alpha carbon and there are no alpha hydrogens, so it can't form the enolet. So we don't have to worry about doing the directed aldol addition, we can just mix these two compounds with sodium hydroxide, and we'll get this aldol product. Okay, here's a counterexample, right? So it's very similar. We have the same ketone, right? It's doing the attacking and adding here. But now the compound that we attacked right, I've just taken this methyl group and drawn it down here, right? So we've attacked this ketone. And this ketone has two alpha carbons, both of which could be the enolate. And so we're going to get a mixture of products if we just try to mix these with sodium hydroxide. So what we need to do instead is start with the ketone that we want to be the nucleophile. And the reagents we need to add is, first, we need to add LDA to convert that completely into the enolate. Then we can do the dropwise addition of the other ketone that we want to act as the electrophile. And then we need to finish it off with a water workup, because the presence of this really strong base LDA is going to deprotonate our alcohol, and so we need to add water to reprotonate, to get rid of that alkoxide ion. And so these would be the reactants that I would need in order to create this addition product. Okay, one last example. Looks like there's a typo. This should be 2,6 heptane dione. Is treated in the presence of sodium hydroxide. A condensation product with a 6-membered ring is obtained, and we want to draw this product. So first, let's see what 2,6 heptane dione looks like. So heptane, 2, 3, 4, 5, 6, 7. I've got carbonyl groups on carbons 2 and 6. And so if we think about which alpha carbon is going to be doing the attacking, if I do this one, it's going to be a 1, 2, 3, 4-membered ring. So that's not going to work. So it's got to be this one, where we're going to deprotonate that hydrogen, and it's going to come around and attack here to give us the alcohol and the aldol addition product. So let's see what that looks like first, and then we can draw the what happens after we eliminate to give us the condensation product. So I think the easiest thing to do here is let's number our carbons. So the one that's doing the nucleophilic attack we'll call 1, 2, 3, 4, 5, 6. And so we can draw our 6-membered ring. And we can start numbering wherever we want. I'll call this 1, 2, 3, 4, 5, 6. So carbon 2 is going to have the carbonyl group. Carbon 6 is going to have a methyl and the alcohol. And so that would be our addition product. And so for the elimination, we're going to want to form the alpha beta unsaturated diketone. So the double bond is going to go there when we eliminate that OH. And so our condensation product is going to be that.